Yeah, hi.
Just tell me.
Yeah. So it's finally working, and we are happy to have Ezra Getzler from Northwestern University. He's going to give a series of 2 talks on Gromov-Witten invariants and the Virasoro conjecture. So, okay.
Yeah, well, thank you very much for making this possible. I wish I was able to be there, but I can't, unfortunately. So here we go. So today I'm just going to talk about the case of Gromov-Witten invariants of a point. This was the theory which Witten introduced in 1991. It was called pure topological gravity. And he made a conjecture at that time, the KdV conjecture. So what I want to talk about today, I'm going to state that conjecture very carefully, and I'm not going to prove it. And I'm going to explain why the KdV conjecture is equivalent to the Virasoro conjecture. So I'll explain that conjecture also. In my next lecture, I'll explain how these ideas can be generalized to Gromov-Witten invariants for projective manifolds. So, there we are. So the KdV hierarchy is a integrable system which was introduced in the 1960s. It's a sequence of commuting nonlinear flows on a potential function. This is called the Hills operator. It looks a lot like the Schrödinger operator. And the flows preserve the spectrum of this Hamiltonian. So this is a tremendously important theory. It was then studied further by Krichever and by Saito, and is now part of algebraic geometry, representation theory, and so on. On the other hand, there's this more mysterious sequence of equations, which are linear differential equations, second-order differential equations, which, however, don't commute with each other. And those give you a completely different way of understanding the equations that hold for the Gromov-Witten invariants of a point. In fact, these differential equations, these differential operators, satisfy commutation relations among themselves, which make them look like the Lie algebra of vector fields on the line. So there was a bit of confusion in the early days of the subject. The Lie algebra of vector fields on the line is a Lie subalgebra of a Lie algebra called the Virasoro Lie algebra. The Virasoro Lie algebra is related to vector fields on the circle, but it's a much more complicated Lie algebra, and the Lie algebra we're looking at is something like a parabolic Lie subalgebra of it, if you like. So that's the setting. The word Virasoro is incorrectly used, and that's unfortunately what the conjecture has become known as. Okay, please feel free to ask questions. I don't know if there's a microphone there, but I hope you'll be able to ask me questions if I am not leaving something out compared with previous lectures you've had. So as I said, in the first lecture, I'm going to relate these 2 equations in the case of pure topological gravity, and then in the second lecture, and perhaps I'll be allowed to have a third lecture if we can work out something, I'll be able to talk about more general, much more important cases like projective space. Okay, so recall that the moduli space of n-pointed stable curves, I left out the word stable, sorry, of genus G with n marked points is a projective variety over C of dimension 3G minus 3 plus n. Its open part is the moduli space of smooth curves of Riemann. In fact, I think you've probably learned that it's not best to think of it as a projective variety, but better to think of it as a smooth and proper Deligne-Mumford stack, or perhaps you've heard the word orbifold. The other thing we can say about it is that if 2g minus 2 plus n is not strictly positive, then this moduli space is simply defined to be empty because there are no stable curves in that case. So that basically covers the case of a rational curve with 0, 1, or 2 marked points, and we'll come back to those. Okay, so denote a pointed stable curve, C, with the marked points Z1 up to Zn, which are in C. Those are n distinct smooth points in C. And hence we can look at their tangent lines, and those are assembled to form line bundles, L1 up to Ln, over this moduli space. And those line bundles have Chern classes. And those Chern classes were introduced by Witten, and he calls them psi1 up to psi-n. In fact, Mumford had written about these classes earlier, but Witten was the one who emphasized their importance on these moduli spaces. So those are the algebraic divisors that we're going to be working with, and we're going to take intersections of those. So Mumford would have loved to have formulas for these. It was Witten who found a conjecture for the formulas for all of these intersection classes. So as I mentioned, this is a Deligne-Mumford stack, or smooth projective variety coarse moduli space associated to a smooth proper Deligne-Mumford stack. So it has a fundamental cycle, which is actually an algebraic cycle, and which lies in the top dimension, 6g minus 6 plus 2n, and has rational coefficients because we have a coarse moduli space here, not a fine moduli space. If the genus is 0, then in fact this is an integral class, okay? And so then Witten's conjecture involves this collection of intersection numbers for which he introduced the notation angular brackets, and that's just his notation for these particular intersection numbers. So we form the monomial in the powers of the classes psi1 up to psi-n, and then integrate over the moduli space. So here are some examples. I had to look this one up. So the case g equals 1 is actually quite well known. The integral of psi1 over the moduli space of elliptic curves completed at infinity is a 24th, and that follows from a standard Riemann-Roch calculation. On the other hand, you can generalize that very beautifully. This was done by Faber and Pander. And so if you look at the top power of psi1 on mg1 bar, you get this beautiful formula, 1 over 24 to the g times g factorial. On the other hand, in genus 0, we have this closed formula for all of the non-zero intersections. We only get a non-zero number if the sum of the k1 up to kn equals 3g minus 3 plus n, which when g is 0 is n minus 3, and then we get this multinomial coefficient. So that was calculated by Witten. Okay, so please write that number down. We'll be coming back to it. Okay, are there any questions? Okay. Now, we're going to form a generating function for all of these numbers. So what we do is for each k greater than or equal to 0, we introduce a variable t sub k. So we have a whole sequence of variables, t0, t1, t2, t3, and so on. And these variables are, if you can think of them as coordinates on an infinite dimensional formal space, which Witten called the large phase space. So this is a somewhat subtle object. Another way of thinking about this, for those of you who know some cohomology theory, is you could think of this as functions, formal functions, on the equivariant cohomology of a point where the circle acts trivially on a point. That's a point of view that I quite like. But anyway, we have this sequence of coordinates, t0, t1, t2, t3, and so on. And we form this huge generating function for all of these numbers, okay? So these are very complicated functions, and these are the functions which Witten's conjecture involves. So for each G genus, we have such a generating function. And for genus 0, I've given you effectively a formula for that function. And now we have all the higher ones, about which currently, until later in this talk, we know much less. Okay? F1, F2, and so on. And then we introduce this Planck's constant, if you like, h bar. Don't think of it as a number. Think of it as a formal power series also, but it's just keeping track of the genus. And we form a big generating function of all of these functions put together. Now, if you do a little calculation, you'll see that F0 begins with a cubic term. It doesn't have any lower terms because M0n is empty if n is less than 3, okay? And then if you look at M03 bar, that's just a point. And so the only intersection number which is non-zero for M03 bar is where you have at the 3 points we put tau 0, if you like. Let me go back a slide there. If you have n equals 3 in this formula at the bottom of the page, then you see that K1, K2, and K3 are all equal to 0, and tau 0, tau 0, tau 0 is equal. Okay? So what that means is that F0 is tau 0 over 6 plus higher. Now we're going to make the central definition full. We're going to take the second derivative of f with respect to t0. Then what you see is we get the result of the baby.
Could you just pause? Hi, yeah, so could you just pause for a second because the audio is...
Absolutely.
I mean, the audio is basically breaking off a bit.
Oh.
Yeah,
that might be partially... Your video came on.
Oh, okay,
I didn't have video before.
Okay.
I like having video, but maybe there's not enough bandwidth to do everything.
Yeah, so we'll switch off the video maybe and we'll continue the usual way.
Are you going to switch off the video or do I have to do that?
No, I think they'll do it. So...
Okay, good. Okay. So where do you want me to go back to?
So maybe you can start from this generating series for F.
F. Did you do FG or do you want me to describe F0 again?
So maybe start with F0 and then continue from there.
Yeah, okay. So Witten introduces this, for each genus G greater than or equal to 0, Witten introduces this huge generating function. And because of the formulas we had on the previous page there, you see that for F0, in some sense, we have a complete formula for F0, although the generating function is not perhaps a standard one. But for the higher ones, we don't yet have terribly much information, and that's the content of Witten's KDV conjecture. So F0 begins with a cubic term because M0n is empty for n less than 3. And so n equals 3 is the very first contribution to F0. So for F0, we're going to have, and then the contribution, because M03 bar is 0-dimensional, the only contribution is where K1, K2, and K3 are all equal to 0. And then the intersection number is just 1. What that means is that F0 begins with T0 cubed over 6, and then higher order terms, quartic and higher. Now, for us, the central object of this talk is the second derivative of, I introduced FG, now let me introduce F. F is just a combination of all of the FG, where I take the sum from 0 to infinity, and I'm just going to include this parameter, which I called Planck's constant. It's not important what we call it, which just keeps track of the different genera. So we have F0 plus Planck's constant times F1 plus and so on. And this combines all of the information of all of these intersection numbers for all genus and all numbers of marked points. And for us, the most important object in this talk is the second derivative of F with respect to T0. That's going to be the basic parameter of the theory. We think of that as the object that is going to flow under the KdV flow. So if you go back to the original, the specification of the KdV hierarchy, U is the thing which the KdV hierarchy is about. And it's just, as I said, the second derivative of F. And what that means is it begins with T0. You can think up to correction terms, it is T0, which is very interesting. And then there are quadratic and higher terms, plus terms which vanish to first order in Planck's constant. Okay? Can everyone hear me now? Am I coming through? Yeah?
Yes.
It's good. Okay, that's good. Okay, now, has anybody in the audience studied integrable systems before? I'm curious. So, no, not so much. Okay, so I'm going to do a crash course in KdV. This is over ambitious. But what we do is we're going to consider, before, you notice, we had polynomials or power series in T0, T1, T2, T3. Now we're going to do something very different. We're going to look at polynomials in U and its derivatives with respect to T0. Okay? So actually, we think of U as a function on the line. The parameter of that line is T0, and we can consider arbitrary polynomials in all the derivatives of U. Okay? You'll see examples of those later. And now comes the remarkable thing. It turns out that just as U is T0 plus higher order terms, the kth derivative of U is Tk plus higher order terms. So roughly speaking, instead of using the coordinates T0, T1, T2 on this large phase space, we're going to use U, the derivative of U, the second derivative of U, and so on, as coordinates on the large phase space. So everything I just said wasn't quite correct, because the first derivative of U begins with 1, and then it has T1 as the next coefficient. All the higher derivatives have vanishing constant term, okay? This is just a facet of the counting of dimensions. So you can prove this already, this formula, because what this formula is telling you is what happens if you are looking at M0n and you have a tau k and all the other taus are tau 0. So in other words, what I'm looking at is an integral on M0 k minus 2, sorry, got that wrong. M0 k plus 2 bar, I'm looking at psi 1 to the k, okay? And I get this, the leading coefficient then is 1. So I'll leave that for you guys to just check. Maybe I should have included the calculation. All right, so there's a standard on this commutative algebra that I've introduced, whose generators are h bar u, u prime, second derivative of u, and so on, there's a standard derivation. And I'll denote this derivation by curly d, and this derivation takes the kth derivative of u to the k plus first derivative, and it kills the constant, power counting, the genus counting variable. Okay? So this is the context in which we're going to introduce the KdV equations. So now I'm going to give a very precise definition of the KdV hierarchy. It's a sequence of nonlinear differential equations that we want to be satisfied by U. Okay, so we have this mysterious differential operator which acts on our commutative ring. We have this commutative ring. This differential operator, capital D, is going to act on this ring. Okay? I hope the formula for this operator is clear. Notice that if I set Planck's constant to 0, this just becomes a very simple first-order self-adjoint differential operator. Okay? Self-adjoint with respect to the Lebesgue measure. And the correction term is an extra term proportional to Planck's constant, which is a higher order derivative. Okay, this is a mysterious operator. This is not the KdV hierarchy, but it has a very specific role here to play. And we're going to introduce these polynomials, which were introduced in the early 1970s, called the Gelfand-Dickey polynomials. So they're defined by recursion. What we do is we start with R0 equals 1, and then recursively we apply the operator capital D to the polynomial Rm, and then that is going to be a total derivative. And the polynomial that it's a total derivative of is Rm plus 1, up to this scaling factor. Okay? So this isn't necessarily the usual normalization of the Gelfand-Dickey polynomials, but it's the one that we're going to use today. It's the most convenient. And so what has to be proved in order to use this recursion is that the left-hand side is in fact a derivative. And that is one of the theorems that Gelfand and Dickey prove. I won't be able to prove that today, but it's proved in, if you like, any book on KdV. So the other thing is that we have to specify the constant term of these polynomials. We're going to say that their constant term vanishes except for R0. R0 is the only Gelfand-Dickey polynomial with non-vanishing constant term. So if you get bored with my talk, you can calculate on just a single sheet of paper. It's easy to calculate these. The R1 is completely obvious from our formulas. R2 will take you about 10 minutes to get straight, and R3 will take you the rest of the talk, perhaps, to get completely accurate. But what Gelfand and Dickey prove is that you can find the solutions to this recursion for each value of n. Okay? So you might want, if you've got a piece of paper handy there, you might want to write down R1 and R2, because we're definitely not going to use R3. Okay? Any question at this point? Okay, let's continue. So recall I introduced this generating function of the intersection numbers, and now I can state Witten's KdV conjecture. Witten's KdV conjecture says that if I take a derivative of u with respect to tk, then that's given by the derivative of this Gelfand-Dickey polynomial, rk plus 1, but after we take a derivative with respect to t0. Okay? So you can see that the first Gelfand-Dickey polynomial is U. And so what this formula then says for k equals 0 is that the derivative of U with respect to t0 is the derivative of U. In other words, it identifies the formal variable that U is a function of with the parameter t0. So that wasn't terribly exciting. But the next one is a difficult equation, deep equation, and that's the Korteweg-de Vries equation. So it says that the derivative of U with respect to this parameter t1 is given by this explicit combination of partial derivatives of U with respect to t0. We have the most important term is U times U prime. And so that's what's called the dispersionless limit. I'll talk about that a bit later. And then there's another term which raises the genus by 1 and involves third derivatives. This is an incredibly complicated conjecture, one which is very mysterious, and there was not very much idea how to solve it. So the Korteweg-de Vries equation, I didn't write this on my slide. It was actually discovered in the 19th century and it came about because of the study in England and the Netherlands and France, I think, of the equations that govern waves in a shallow canal. I guess during the 1830s, 1840s, 1850s, a lot of canals were made, and so people got interested in how water moves on canals, and observations were made that the motion was different from that in the open sea. So that's how the Korteweg-de Vries equation came about. It turns out it was actually discovered originally in the 1870s and rediscovered by Korteweg and de Vries in 1893, and then almost completely ignored until the 1960s. Okay, so this allows us, the conjecture allows us to extend the derivations delta k to the whole ring that we're looking at. And what we require in order for the conjecture to make sense is this integrability condition. This integrability condition is the fundamental relation which makes the KdV hierarchy important. It's the complete integrability, and this is one of the major results of the theory of the KdV hierarchy. So this would be proved in the first couple of lectures if you did a course on the KdV hierarchy. It doesn't take very long to prove. The best proof uses the Lax equation for the KdV hierarchy, but I'm just going to tell you that those equations hold, and as a result, a priori, the operators delta J and delta K commute with each other, which of course is absolutely essential if the conjecture is to make sense, because for the conjecture to make sense, we need that differentiation with respect to Tj and Tk have to be commuting operators. So Kontsevich proved the KdV conjecture in 1992. His proof is utterly remarkable because it uses a combination of different ideas which I don't think anybody else would have, at least at that time, thought of assembling together to give a proof. Another extremely beautiful proof was given by Mirzakhani about 10 years after that. And there are a number of other very attractive proofs using Horowitz covers, and there's another proof of Okounkov, which uses the Toda hierarchy. But I personally think that Mirzakhani's proof, which is not using algebraic geometry, but rather uses hyperbolic geometry, is a particularly conceptual proof. none of the proofs are easy. This is, by any standard, a very difficult theorem. And this theorem is, in some way, separate from other theorems in the subject. Its proof does not resemble that of other theorems that in the subject. Okay, so my goal is to show you how this conjecture can be reformulated as the so-called Virasoro conjecture. But before I do that, let me show you what happens to this conjecture when we set Planck's constant to 0. In other words, we're only going to look at the genus 0 part of the conjecture. And in that case, the Gelfand-Dickey polynomials simplify tremendously. They just become the powers of U. And the KdV conjecture just becomes this very simple conjecture, which, if you want, maybe in the evening, if you're feeling jet-lagged or something, you can try to prove. Okay? So notice you can integrate this conjecture once with respect to T0, and it becomes this formula. Okay? The formula for k equals 0 is just the definition of U, and the formula with higher k is the statement that the KdV conjecture. Okay? So in this form, this conjecture becomes maybe one of the fundamental subjects of the generalizations which were given by Giventhal. So remember this formula because this will, you don't have to remember it because I've given the organizers my slides, and so hopefully you'll be able to see copies of my slides. But anyway, remember this formula because this is a formula Giventhal will generalize later. Okay. So now, the Virasoro conjecture is going to concern, hello? Yeah. The Virasoro conjecture is going to concern a sequence of linear operators, linear differential operators, and the very first of those is proved in a way which is different from the others. So before going to the Virasoro conjecture, I want to talk about this basic equation. It's called the string equation, and it concerns these fibrations introduced by Knudsen and Mumford between the Deligne-Mumford moduli spaces. So I'm curious, were these already discussed at all in this week or not yet? I'm the first one to talk about it.
I talked about it in one of his talks.
Oh, good. Okay. Who did, sorry? Who did?
Chitrabhanu Chaudhary.
Oh, good. Okay. Yeah. So, yeah, well, that's, that puts a smile on my face because I still remember when we studied it at Northwestern. Anyway, so this is a morphism which conceptually is easy to state, but actually its careful study is remarkably complicated. But let's not worry about the complications. Let's just pretend that it's easy to understand. The basic idea is that if you have a stable curve of genus G with n plus 1 marked points, you can try to forget the last marked point. So we have C, we have Z1 up to Zn plus 1, and we're just going to forget Zn plus 1. The problem with this definition, you see it works if C is irreducible, because then the new curve will still necessarily be stable, at least if 2g minus 2 plus n is greater than 0. But it's possible that after you forget Zn, if the curve is not irreducible, that one of the components of C becomes unstable. That is, it now may have continuous deformations, continuous automorphisms. So in that case, what we have to do is take that component, which will necessarily be a rational component, and we have to contract that rational component to a point. So this is where the study of this morphism becomes quite complicated, to show that it's a flat morphism. And there are three cases. One in which the rational component has two double points that so it's joining two double points on other components of the curve, and when we contract it, it takes the two sides of those two double points and joins them as a single double point now. So what happens in that case is we lose a double point. There are two other cases where the rational component only has one double point, and it either has 0 or 1 marked points. And so when we contract such a rational component, in the first case where there's 0 marked points, we simply erase that, that rational component from the curve and forget about the presence of that double point. In the case where the rational curve has a double point at one side and a marked point on the other side, we contract the rational component and we're just left with the marked point at what was the double point. Anyway, that's quite complicated, but the basic, the ultimate conclusion is that the fiber of this map at C is naturally isomorphic to C. And so you can see from that that it's a flat morphism. The fiber at each point is a stable pointed curve. And so Witten, studying this fibration, he was able to prove the string equation. If we're in the stable setting where 2g minus 2 plus n is greater than 0, then if we put tau 0 at the new marked point, in other words, if we just have psi n plus 1 to the 0, we don't in fact put any powers of psi n plus 1 in the intersection, then that's equal to a sum of n terms, in each of which the number of the power of psi I is reduced by 1. Okay? So that's Witten's string equation, or it's also known as the puncture equation. And we can rewrite that as a differential equation for the generating functions fg, which is a little bit different for f0 and for the higher fg. Notice that for f0, remember that f0 begins with 1/6 of t0 cubed. So when we take the derivative of that with respect to t0, we see that it begins with the quadratic term 1/2 of t0 squared. And so that's an exceptional case which we have to put on the right-hand side. But apart from that, you see that the left-hand side is just capturing the effect on a generating function of these equations. It converts the series of all of those equations into a single differential equation for each fg. Okay? So this is the string equation, and we can rewrite that as a single equation for f by summing this over h bar, over powers of h bar. And then we're going to actually rewrite the string equation. We prefer to rewrite it as an equation not for f, but for this formal expression in terms of f, which is actually inspired by the theory of the tau function for integrable systems. So I'm not going to go into what tau functions are, just suffice it to say that if you try to understand the role of this expression, capital Z, in the theory of intersection numbers, you'll be getting an idea of what the tau function is in the theory of integrable systems. So it's very important to notice that this expression is, formally speaking, the generating function for not for intersection numbers on connected stable curves, but intersection number on moduli spaces of possibly disconnected stable curves. So imagine that we're going to look at the moduli space of possibly disconnected stable curves of Euler characteristic 2 minus 2g with n marked points, n smooth marked points. Now g could be 0, could be positive or negative, because the Euler characteristic can be in fact any even integer. But actually you can prove, follows from the definition of stability, you can prove that for each g and n, this moduli space is still proper. It has many components, but it's still proper. And we can form this intersection number, and in that way we get a new sequence of rational numbers, and z is their generating function. Okay? So in terms of z, the string equation just becomes a linear differential equation for z. And so this is one of Witten's main intuitions, that working with z rather than fg simplifies the equations that are satisfied. So you see that this is a inhomogeneous first order differential equation. It's a vector field, that's the first two terms, plus a quadratic function. Okay? So this is the simplest of the differential operators which are going to occur in the Virasoro conjecture. The remaining operators are going to be very complicated. So please forgive me that we're going to have such complicated formulas. Okay. Any questions about this? Okay. I'm a bit worried that I'm not being asked any questions. Is that because my talks are a bit more advanced than the background, or don't know? Any? I'd love to have some questions.
I would say that people are mostly following what you're saying so far.
Yes.
Maybe they might.
Good.
Maybe they might have some questions along the
Okay.
like later on.
I think they will. Okay. There's plenty of time. Okay. Good.
Ezra.
Yeah.
So I had
Yes.
a couple of questions. So first
Good.
question is, so that expression z is e to the power h inverse f. So is there some heuristic reason why one ought to consider this? I mean, I know everything works out once you take.
Yeah, that's a very good question. Yeah. Yeah. So to be honest, So my basic answer would be that to some degree, we're looking at some sort of analog of quantum theory. And in quantum theory, it's not the action which is important, but the exponential of the action which is important, because that's the integrand in the Feynman integral. So somehow, although in classical physics, we study the logarithm of the exponential of the action, and we call that the action, it's exponential, which is the fundamental object of study in physics. And somehow, in the theory of integrable systems, it's perhaps a similar thing. In the theory of integrable systems, for KdV, this object was introduced by Saito. I think he introduced it simply because it converts nonlinear differential operators into linear differential operators. Is that a good answer?
And I had a second question. Maybe you'll say more about this later, but as you
Yes.
pointed out, this KdV equation, it originated because people were studying water waves. So I know there are now proofs by Gonsalves, etc. But do any of these proofs shed light on this mysterious fact that, why KdV equation appears in this study of intersection
Yes.
numbers on moduli space?
Yes. Yes. I'll answer your question, and then I have to take a 2-minute break because I have to plug in my computer. Okay. So No, this doesn't shed any light on the classical theory of KdV. In both theories, this sequence of commuting Hamiltonians, the Gelfand-Dickey polynomials, play a very important role. But in the analytic theory of KdV, you're going to have to use those. That's just the beginning of the subject, and you have to use these conserved quantities in clever ways. Whereas here, these solutions are only formal power series, so they don't have any analytic content. So somehow the formal nature of the subject is very similar, but currently we don't have any close link between the. But why don't you send me an email, and I'd be happy to try answering your question, maybe in a Skype, one-on-one Skype some other time or something, because I can say more about Witten's original work. I don't know if you have a physics background, because what happened was this is related to work of, I've forgotten exactly who. I think it was Gross and Migdal, and Douglas and someone. Sorry, I don't remember the exact people who did these papers in 1991 or 1990. What they discovered was that the theory of orthogonal polynomials led in a certain limit to this KdV equation. And so that was interpreted as saying that the study of random triangulations in some limit led to the KdV hierarchy, but it's a very formal calculation that that leads to that, and doesn't have much to do with the original theory of KdV. A different way of answering it is that there are only very few equations that somehow come up again and again in physics, which correspond to fixed points of universal hierarchies, and somehow this is one of them, I guess. That's not a very good answer. Did I answer your second question?
Yes, you answered my question.
Okay, good. Thank you. Okay, so we had the string equation, L minus 1z, and now let's take a second derivative of this equation and see what we get. So when you take when you apply the differential operator second differentiation with respect to t0, you obtain a string equation for u. Remember that we said that u itself was t0 plus higher order terms, and the string equation actually expresses that. It says that the derivative of u with respect to t0 is 1 plus some higher order terms. So the string equation is this very algebraic expression of the leading order of u. So it's going to be one of the fundamental equations. And so before we had the KdV hierarchy, which gives you formulas for the derivatives of u with respect to tk. And combining that with this asymptotic as we go to 0, namely that it's t0 plus higher order terms, that gives a complete characterization of u. Okay? So the KdV hierarchy says that completely characterized function u is the generating function of Witten. However, it's not obvious that there is any solution until you've proved the KdV conjecture of Witten. There might not be any solution whatsoever. So I want to say a few words about how you know there's any solution at all without proving Witten's conjecture. So Kontsevich, in the course of proving the KdV conjecture, one of his main results in his paper in 1992 was to prove that there is a solution of the KDV hierarchy satisfying the string equation. And later, another proof, which uses representation theory of loop groups, so it's closer to Saito's work on the solutions of the KDV hierarchy using tau functions. Maybe I'll just say in words, Saito identified tau functions as points in an infinite dimensional Grassmannian. And that Grassmannian is some sort of flag variety for a loop group, an infinite dimensional group. So that immediately, I think, electrified people in representation theory, because there's a close relationship between loop groups and reductive groups for the p-adic field and more generally for discrete valuation fields. So the non-Archimedean case. But anyway, back to Katz and Schwarz. So they were able to also prove that there is a solution. But it's not at all an elementary fact that there's any solution whatsoever. It is, however, straightforward to see that there's a unique solution, if any, exists. So I just wanted to show briefly how Kontsevich shows that there's a solution. He expresses the solution as a integral over the space of n by n Hermitian matrices. So we take the space of n by n Hermitian matrices and we put this family of Gaussian measures on it. And then, so for each lambda, each Hermitian positive definite matrix lambda, we have a Gaussian measure. And then we integrate this complicated function, an exponential of a cubic expression in the matrix, we integrate it with respect to this Gaussian. So that gives a function of lambda, and Kontsevich shows that that function of lambda only depends on lambda through the traces of the odd negative powers of lambda. And he then shows that as you take the rank of these Hermitian matrices to infinity, this converges to a solution of the KDV hierarchy, which furthermore satisfies the string equation. So that's a remarkable result, and this Kontsevich matrix model is still considered an extraordinary discovery. Okay, so yes.
Just to be sure I'm following correctly, that m is the variable of integration?
Yes, that's right. Yes, I'm sorry. So I should have, on that second display, it should be d mu lambda m. Exactly. Yeah. Yeah, so we're integrating over m. Capital M. Yeah. Yeah, I mean, it's almost impossible to believe this result. It's very, very confusing. It's like mathematics done by somebody who really understands physics, I would say. Anyway, I don't think I could. Yes, please.
Sorry. This matrix model solutions, are these also formal solutions, or are they? So the formal solution is the power series.
Yes.
And the same for the what was the previous one with the loop groups?
In that case also, only a formal power series. Okay. I'll talk a little in my second lecture about, so actually, so I was skipping ahead a little. It turns out that for g greater than 0, fg is itself a differential polynomial in U. So each fg can be determined by a finite amount of information. It's just a polynomial of a certain degree in a finite number of the variables that generate our commutative ring. Whereas Z is this extremely complicated object that depends on all of the variables simultaneously. So here, where we're using representation theory, it's very difficult to unravel that formal dependence. And it's really more a part of Dubrovin's theory, in which the polynomial dependence on derivatives of U takes center stage. Okay? So that'll be more a part of my second lecture. I want to say in advance that I'm very optimistic that I'll be able to give my second lecture, but I unfortunately can't promise. But in that case, I'll send you the slides. Okay, but let's not talk about that anymore. Okay, any more questions? Good. So now I'm going to show you the second equation of the Virasoro conjecture. This is also due to Witten, and it again uses this flat fibration, which we introduced a moment ago, of forgetting the last marked point. And then, using the Riemann-Roch theorem, you see that if we introduce a single power of psi n plus 1, just the divisor at the new marked point, so that means put a tau 1 operator, that just gives us the Euler characteristic of the punctured curve. So you could view this as an expression of the Riemann-Roch theorem in a sense. And again, there's going to be an exception for this formula in the special case where G is 1 and N is 0. So that's the borderline case. And in that case, we already know that the tau 1, just the single angular bracket tau 1, is a 24th, and we'll use that in a moment. Now, if I multiply this equation by 3 halves, what have I done wrong? Oh yeah, nothing. If I multiply this equation by 3 halves, then I get, on the right-hand side, 3g minus 3 plus 3 halves times n. Now, 3g minus 3 plus n is the dimension of the moduli space, which is k1 plus k2 plus up to kn. So I've substituted 3g minus 3 plus n is k1 plus k2 up to kn, and I've got half n left over. Okay? Is that calculation clear to everybody? And now I'm going to take these formulas and similarly to the way that we manipulated the string equation, we're going to get a single differential equation for Z.
Ezra?
Yes. Yes. I'm sorry? Oh, no. Okay. Oh, is this blocking? Oh. I was scared if I closed the window that it would close the... Okay, good. Sorry about that. I didn't realize you could see it. That's really silly. Okay, I would have closed it ages ago. Of course, so I'm not getting your video right now, but if I was, I wouldn't be able to see you anymore, but I saw you before, so that was nice. Okay, so now I'll skip ahead and just write the differential operator L0, which is the expression of these equations on the generating function Z. Okay? So this is already quite a bit more complicated than L minus 1. And you see that there's a constant term this time. In the case of L minus 1, we had a quadratic polynomial. Now we get a constant term. And I want you to notice that this constant term has the power of Planck's constant h bar to the 0. And that 0 corresponds to genus 1. It somehow corresponds to the fact that elliptic curves have Euler characteristic 0. Okay? Anyway, there's a lot of details in deriving this equation, but they're not terribly difficult. Nothing like what's about to come. So now things get extremely complicated. And here, at this point, we need 2 Fields medalists to take us the rest. Sorry, 3 Fields medalists to take us the rest of the way, namely Witten, Kontsevich, and Mirzakhani. Okay, so this is for n greater than 0. These are the operators which Witten introduced. And the Witten conjecture, the Virasoro conjecture is going to say that if I apply the operator Ln to Z, then I get 0. So I'll actually give you an indication of how it's proved on the last slide. So I'm going to tell you a little about how to understand these operators because they have a very complicated formula. So for those of you who've done some physics, you'll know the idea of a field, a free field. It's a generating function involving oscillators. And in our case, the oscillators are the multiplication by tk, where k goes from 0 to infinity. And then, so those are the raising operators, and the lowering operators are the derivatives, delta 0 to up to delta 1, delta 2, and so on. So with some fudge factors, we get these this free field. There's a peculiar correction term at the end, which corresponds actually to a mysterious shift in the variable t1. We're actually going to be thinking about t1 not expanding it around 0, but expanding it around 1. If you saw before that there was a shift for t1, which was a bit different from the way the other variables operated, and that corresponds to this mysterious shift here. Okay? So the way we use the free field, it's a generating function for operators, and thinking of ln also as a differential operator, we're going to take their commutator in the Lie algebra of differential operators. And then we get this basic characterization of ln. The point is that this completely characterizes ln up to a constant. And then you can further argue that the constant is going to be 0, except for L0, for which you have to calculate the constant more carefully. So this equation now, using the Jacobi rule, we see that the commutator of Lm and Ln is going to be m minus n times Lm plus n, plus some constant, constant multiple of, well, when I say constant, I mean actually an arbitrary power series in Planck's constant h bar. And you can check that that's 0 except when m plus n is 0. And in that case, you have one calculation you have to do more carefully. You have to calculate the commutator of L1, which is this very complicated expression, but in the slightly simpler case where n is 1. So in that case, the last line, there's only one term. And when you do the calculation, you see that you get that 1/16 exactly as is needed. So that 1/16 in L0 is somehow absolutely essential for the whole theory to work. If we had a different constant, then we'd get a contradiction between the fact that L1 commutator L minus 1 annihilated Z on the one hand, and L0 annihilates Z. If both sides of this equation annihilated Z, but the constant was different, then we would see that multiplication by a non-zero constant annihilated Z, and hence Z was 0. So this equation that I've written here at the end of the page is somehow absolutely essential for everything to work. Okay, so the Virasoro conjecture states that Ln applied to Z vanishes for all n greater than or equal to -1. Now we have these commutation relations among the Ln, and so it turns out that actually L2 and L minus 1 between them generate the whole Lie algebra. So since we already know that L minus 1 annihilates Z, it suffices to prove the Virasoro conjecture to check that L2 annihilates Z. Now that observation is somehow, it sounds like it's going to be really useful, but as far as I know, in the 25 years since this subject began, nobody has ever been able to make any use of that simplification. It's not easier to understand L2 than to understand all of the constraints. And in some sense, it's easier to understand all of the constraints together than to understand any one of them. Okay. So like the KdV conjecture, the Virasoro conjecture completely determines the generating function Z, and that implies that the Virasoro conjecture has a solution, namely the solution of the KdV conjecture. But again, it's not at all obvious that the Virasoro conjecture, that there's any capital Z, which satisfies these constraints. And again, that follows from Conjecture's formula, explicit formula for Z as a matrix integral. As a matter of fact, it's probably easier to prove that his matrix integral satisfies the Virasoro conjecture than to show that it satisfies the KdV conjecture. Okay, just out of curiosity, I'm showing you here how the Virasoro conjecture can be rewritten just as a sequence of conjectures for the Fg, individual functions Fg. And what you see is that it gives you a vector field applied to Fg is equal to some differential polynomial in the lower f, the f0 up to fg minus 1, okay? So this becomes very important in further application of these equations, but I thought I'd show you, since the whole Virasoro conjecture is quite unappealing because it's so concise, this sequence of equations is what it really says, okay? And now I come to my last slide for today. So this is the theorem of Dijkgraaf, Verlinde, and Verlinde, that if Z satisfies the string equation and the KdV equation, then it satisfies the Virasoro conjecture, and vice versa. And I'm just going to give you a hint of how the proof is given. In fact, if you look at my 1998 paper on the archive about the Virasoro conjecture, there's a section in which this is done in great detail. So I've left out any more details now because it's a little overwhelming, all the algebraic calculations. But it's the kind of theorem now that I'm going to tell you how it goes, that a chimpanzee should be able to do. You just have to put one formula in front of another and you'll get this. So the first lemma that we need in order to prove the result is this basic lemma that if a function is annihilated by L minus 1 and is independent of T0, then it's automatically a constant. So we use that lemma over and over again in order to show that certain recursions have as their solution just the function 0. And the second lemma says, let's introduce this formal function little zk, which is the Virasoro constraint. So I'm rewriting the Virasoro constraint in a way that was actually, this is little zk is the generating function for these equations. And now if the KdV conjecture holds, then we also get a recursion in a similar way to the Gelfandiki polynomials for the Virasoro constraints. And so since we know that little z minus 1 vanishes, that's the string equation, we see by recursion that the second derivative of zk plus 1 vanishes, and then using the first lemma, you're able to show that it's a constant, and then you can show by power counting that that constant has to be 0, except for the case k equals -1. For little z0, you have to check what the constant is very, very carefully, and we've already done that. So there we go. So that's the first lecture. I'd be happy to answer questions. Perhaps I can bring the video back so that we can, yeah. Oh, good.
Actually, a very basic question. So the first I1 integrated on N1.
Can you? I can't quite hear. Sorry.
Oh.
Yeah.
Hear me now?
Yeah.
Okay. Yeah. So it's about the integral of the first. So psi1 integrated on this M11. You said that many times. It's 1/24. I was just wondering if you can just give a brief geometric meaning of that, because I know it's somehow half times 1/12.
Absolutely.
And
yes, absolutely.
And that 12 is the number.
So, yeah. So this is very subtle, of course, because the Deligne-Mumford stack M11, it's the fundamental class is really 1/2 times the fundamental cycle that you would think from the coarse moduli space. So that's because every elliptic curve has a involution, the elliptic involution, and so the stack is what do people say? It I can't remember. There's a gerb or something. Anyway, so the answer we're going to get is 1/2 another calculation, which is a 12th. Now let's see if we can do the calculation. I mean, the basic idea, is that let's see. I mean, this is very closely related to the statement that the differentials on the moduli space is modular forms of weight 2. And so, let's see. And so you have to relate. Yeah.
12
I'm not doing so well. But anyway, it's closely related to a standard calculation involving the question of the differentials on the moduli space correspond to so if you raise that to the power 12, then that is the line, that's the divisor which has precisely a single non-trivial section. So it's the 12th power of the differentials has degree 1. So this divisor has degree a 12th, and on top of that, we are dividing by 2 because every elliptic curve has an automorphism, an involution. I'm being a bit hand-wavy, but that's the basic reason. Does that help?
Verify what that 12 is also, just rephrased in a different way, it is the number of rational cubics through 8 generic points. Is that, that number also happens to be 12. Are these two 12 the same 12s? Or
I don't know. If you can relate that to the fact that the lowest dimensional cusp form in the theory of modular forms has weight 12, then yes, we're in business. But I don't know how to show that. Yeah. So it's related rather to an analytic fact, which is the existence of this beautiful object, the cusp form delta.
are there other questions?
So this is more of a philosophical question, but do you think, so I'm not sure, but is Kontsevich proof, so does it yield other mathematics also, or, of the video?
Oh gosh, just you're seeing. Am I sharing my screen? I hope not. I just got a pop-up news item on my screen. Sorry, go on. I lost track of your question. Koncevich's proof philosophically, what?
Does it relate to other mathematics too? Or, has it been used elsewhere to prove?
Oh Lord. That's a really hard question. Okay, so the right person to ask a question like that is Vonkin. Probably not me. No, somehow, isn't that annoying? That's the only direction in which, as far as I know, it could really give additional results. I am ashamed to say that I'm not so much of an expert on the approach of, let's say, Okhunkov and Pandurapande, which really relies on more algebraic, geometric ideas. Just for people who aren't sure about this, the thing about Koncevich's proof is that it uses a remarkable cellular decomposition of Teichmüller space, but this cellular decomposition is real analytic. It's not complex analytic, so it has nothing to do with algebraic geometry. It sits completely outside algebraic geometry. Whereas I think is it fair to say that the proof of the Toda conjecture of Okounkov and Pandey only uses algebraic geometry. And then Okounkov has proved the KdV conjecture using the Toda conjecture. So if you're willing to learn a much more difficult, a much deeper even theorem than the KdV conjecture, which is the equivariant Toda conjecture, then finally you can recover, I think, Koncevich's theorem. But no, I think rather people are still trying to understand the nature of the mathematical objects he introduced because they're so new and exciting. I would say, didn't you have the impression that Mirzakhani's proof puts Koncevich's theorem in a new light, which is very, very revealing? It sort of puts his results more at the center of mathematics.
Yeah, and she doesn't use too much of higher, I mean, she uses her papers are very self-contained, I think.
Yes, yeah. So, and she doesn't use the cellular decomposition, really. She has a more ad hoc partition of the modular space, which probably, if somebody was very careful, maybe it could even be related to these other, because ultimately what we're talking about is different partitions of the Teichmüller space, which are real analytic, and she has such a partition, but she is explaining to you, as it were, in words, using dynamics, what her partition is. And she's not using Strebel differentials. But now we come to the fact that I haven't looked at her proof in a very long time, so yeah. Okay.
If there are no more questions.
Costello has a paper where he basically gives a algorithm to, given any genus G, Gromov-Witten invariant, you basically boil down to a question of zero invariants. Can you hear me?
Mm-hmm.
Genus
yes, I can.
Invariants of a symmetric
yes.
power, and even for so potentially
yes.
if you apply that for a point, at least you can verify Witten's conjecture. So I just wanted to know, is
yes.
that another proof of Witten conjecture, what Kevin Costello does?
Oh, Lord, you've put me on the spot. I doubt it. So there's something missing in what you said, because to get the Gromov-Witten invariance, you still need to know a trivialization of a certain circle action. You see, what happens is that Costello's approach is discussing the cyclic homology of a certain Calabi-Yau algebra, A infinity, I don't know, Fukaya category, let's say. And the point is that the circle action, there's a certain circle action, algebraic circle action on that cyclic homology, which is trivial in homotopy. But what is needed for this calculation is an explicit trivialization. So you need the homotopies. So you need formulas for the homotopies. And I think you're going to need Koncevich's work to get explicit formulas for the homotopies. And once you have those, you can get the theorem. But it's a bit circular. So a reference for that is Telemann's proof of the Virasoro conjecture. So if you go through, what you will see is Telemann's proof really is all about understanding the trivialization of the circle action. Okay?
Thanks. So if not, let's thank Ezra for a nice talk.